Hemispherical lateral variations at the top of the inner core have been verified by a number of quite different seismic data and observations, as well as in dynamo simulations that attempt to predict lateral variations in growth of the inner core from lateral variations of heat transport across the core mantle boundary. In this slide, we summarize some of these quite different variations of types of data and observations sensitive to hemispherical variations, or at least reveal it. At the top is a thin low velocity zone at the top of the eastern equatorial region of the inner core, revealed from multipath P waves. The next figure is zones of intense backscattered P waves from the top of the inner core, from a study by Leighton and Koper. The high backscattering region here in the central equatorial Pacific virtually guarantees that part of the inner core attenuation must be not just viscoelasticity but also scattering, at least in this region. Finally, the well-known hemispherical dichotomy of a fast eastern hemisphere, slow western hemisphere, highly attenuating more attenuating eastern hemisphere, less attenuating western hemisphere, that's been well documented. And the bottom figure are the inner core growth anomalies predicted by Aubert et al.'s simulation of the effect of laterally varying heat transport across the core mantle boundary, predicting a strong, a cold cyclonic downwelling in this region of the inner core. And I believe there's a great deal of correlation in these quite different observations. It's hemispherical, but in detail, quasi-hemispherical, but in detail, it's a little bit more complicated than that. I'd like to digress a little bit to one of these observations, where we found multipathing in this portion of the eastern equatorial hemisphere from P waves sampling the top of the inner core, and we looked at this little complex feature in these waveforms that we do not see in other regions. In order to predict this effect or model it, we have to very carefully model the source time function, either through empirical observations of P waves where structural effects are small, or from direct inversion of the source time function. It can be modeled by a thin low velocity zone with some small or more rapid change in velocity with depth in a zone ranging from 10 to 40 kilometers of depth. The reason I review this earlier work is that this is the region where we also see evidence of a low shear modulus at the top of the inner core. This Eastern Asian equatorial region of the inner core, predicted from dynamo simulations to be a region of active inner core growth. You saw this slide in a previous talk by Tanya. This is a study that we did a year or two ago, where we find a more complex variation of attenuation and velocity across the inner core, not hemispherical, but rather at least three separate zones. Over 2/3 of the inner core, we see a correlation between velocity and attenuation that's opposite to our experience in the mantle. However, in this region of the eastern and central Pacific, we see a region where low velocity correlates with high attenuation in a manner similar to what we see in the mantle. And this is also the region where Leighton and Koper see strong backscattering of energy by volumetric heterogeneities in the inner core. We think this region might be explained by partial melting to explain both observations. The rest of the attenuation may instead be governed by microscopic mechanisms and smaller scale lengths. Shown below is a summary of seismic velocities, showing that seismic velocities, at least in the equatorial regions, have the familiar slower western hemisphere and faster eastern hemisphere with a fairly predictable variation. So the attenuation structure and also the anisotropy structure that people are seeing is more complex than hemispherical. Here's another dynamo simulation by Gubbins and others, again, starting from the assumption of laterally varying conductive heat transport across the core mantle boundary, controlling growth and this time melting of the inner core, where the hot lower mantle of the Pacific actually makes it possible to heat up the inner core in this region and melt part of it in the Pacific region. And they predict two narrow zones of downwelling circulation in the outer core associated with freezing of the inner core, and two narrow zones. It was interesting to see in one of our studies where we looked at travel times and P velocities in the inner core, and we didn't purposely chose these bins to agree with Gubbins' prediction, but we see the fastest zone is actually coincident with their zone of predicted freezing, and the secondary zone has fast velocities at least below 150 kilometers depth, and below that depth range is actually the second most fastest region, so which was quite surprising. This melting region actually was also explained in their study to be a mechanism to make the F region of the lowermost outer core by having an iron-enriched region, which Hernlin will speak about later today. Shown also earlier today was the pre-melting effect to explain the low shear velocity throughout the inner core in the talk by Vocadlo. And I chose this slide to actually illustrate the behavior of the shear modulus near the inner core boundary, where it might be possible actually to have a near zero inner core shear modulus right near its boundary in a thin zone. And a suspicion of that was this multipath, the low velocity zone we saw in P waves. And the next slide, I'm going to review direct evidence for low shear modulus near at least some regions of the inner core boundary. And we discovered this phase PK double IKP, which is underside reflection at the inner core boundary. This can be observed at antipodal range. P waves grazing the top side of the inner core boundary are nearly insensitive to the shear modulus. You have anything between 0 and 5, and it's not going to make any difference. But this particular in the amplitudes or the waveform, this particular wave, though, is strongly sensitive to the shear modulus because its polarization parallel to this P ray is such that it can generate a strongly converted shear wave downwardly, near vertically propagating in the inner core, eventually arriving as a PK-JKP phase. Rarely seen, but it can be, theoretically be there. And because of this easy conversion, shown here is the amplitude reflection coefficient as a function of angle of incidence, you can have a nearly factor of 3 amplification at antipodal distances, which occur in this takeoff angle range here. Also verifying this are synthetic seismograms shown at the right here, where we have a 0 shear modulus at the inner core boundary versus 3.5 kilometers per second. And you can see strong amplification of the double I phase throughout the antipodal range, and very strong exactly at the antipode, where we have also the antipodal focusing effect. So can you actually see this in data? Well, there are several antipodal seismograms, single station observations, but I think they're very powerful. One example is Tonga Kermadec to a station in Algeria, Tamanrasset, a geoscope station, where we see a very strong double I phase compared to the direct PK-IKP, more than 1.5 times its amplitude. And for another antipodal event, these are nearly at 180 degrees to within half a degree. We see no evidence of a double I. Shown here are the double I array paths in the inner core projected up to the surface at antipodal range for this state source receiver distance. And you see the red dots here are the reflection points at the inner core boundary. And you see that they very strongly sample the thin low velocity zone and P waves we detected with multipaths in an earlier study. This event, however, very poorly or doesn't sample this thin low velocity zone as well as with P waves, and the few bounce points, reflection points that do sample it are in regions where this multipath was only controlled observations by maybe 1 or 2 examples. So to further verify this observation more carefully, to look at secondary features of the antipodal double I waveform, we tried to model this Tamanrasset event. Here's a picture of what the vicinity of that station looks like in the Algerian oasis city, geoscope station. We modeled the source time function very carefully, looking at P waves at ranges where Earth structure is unimportant. To get the source time function, convolved it with a broadband velocity waveform to make this synthetic here to compare with the data. We haven't got the frequency content quite right yet because we have a little bit too much intercore attenuation in this example, but we believe this is a strong evidence of a double I that's strongly amplified here, particularly in the secondary waveform features that seem to match those well in the data, even though we have strong noise here, both preceding it and signal-generated noise. So we really do think this is a strongly amplified double I phase. So in conclusions, we've shown or demonstrated, at least with one or two examples, that the double I phase is very sensitive to the shear modulus at the inner core boundary. Can be observed at antipodal recordings that sample a region beneath the equatorial eastern hemisphere in East Asia, or near the eastern edge of the Indian Ocean, predicted to be a region of a freezing inner core and dynamo simulations. It might be, however, a melting region in the convective translation hypothesis. However, the shear modulus can be low, possibly near either a freezing or a melting region, and it will be important to verify with theoretical or experimental work what the difference in scale lengths of solids and liquids in a melting versus a freezing region to distinguish between these two possibilities of low shear modulus. Observations of inner core scattering and attenuation will be key to revealing what these large and small scale lengths would be. And so far, there's an unknown linkage of these lateral variations in shear modulus to mechanisms of elastic anisotropy and differential rotation. And I might point out here, a lot of the seismic observations are mainly equatorial. There are very few polar paths, so I haven't mentioned anything about anisotropy. Future work, we want to use antipodal arrays, particularly those that are now available in Morocco, which strongly sample the antipodal region. Some examples here where we can see double I coming around from two different directions. By carefully modeling the shapes and amplitudes of these, we might, and also the azimuth of approach of a vespogram analysis, we may be able to say something more about constraining which areas of the inner core are freezing and which are melting. Thank you.
We have plenty of time for questions.
How thick do you think the layer of this very low shear modulus would be? Because you know normally the inner core is solid, so at some point it must have a...
Right. How thick is this low shear modulus region would be? We need to do some experiments, maybe some simple reflectivity experiments with transition zones to see how thick it needs to be to make the strong double I amplification. But if it's a coincident with the P multipath region, that region was about 10 to 40 kilometers thick where we could detect it.
Other questions? All right. Thank you, Vernon.